Okay, in the last lecture, we have discussed the barrier tunneling. So, what we have learned in the barrier tunneling, so simply we have seen that the particle, according to the de Broglie hypothesis, the particle has a dual nature, wave as well as particle nature. So in the wave nature, if we say that this is the particle, this may be the any particle, maybe the electron. If this electron is coming as a wave, and in the here, if the energy of this wave, the kinetic energy of this wave is less than the potential energy of the barrier, which we call it as a V naught, even though this particle can tunnel through this barrier, and this effect is known as a tunneling effect. It means this tunneling effect of the particle is because of the wave nature of the particle. Because in the wave nature, if the energy of the particle is even less than the energy of the barrier, even though the particle can penetrate into the barrier, and which we call it as a tunneling effect. So now we have to look at the quantization of the different quantum numbers. So now we know that there are certain quantum numbers. So when we are discussing the particle as a wave nature, then there are certain quantum numbers which has to be followed by the particles. Number one is known as a principal quantum number. So what is the principal quantum number? So in the principal quantum number, which is designated by a term n, and this principal quantum number is representing the different shells. This may be the K shell, L shell, M shell, and N shell, and so on. It means for K shell, the principal quantum number n is equal to 1, for this n is equal to 2, n is equal to 3, and n is equal to 4. So these are the different 4 quantum numbers and so on, which represents the different shells. And this quantum number is known as a principal quantum number. This principal quantum number tells us the position of the electron from the nucleus. It means it shows the radius or position of the electron from the nucleus. It means it identifies the position and the energy of the particle. Of the electron in the orbitals. So this is known as a principal quantum number. The second quantum number, you may call it as an azimuthal quantum number or angular momentum. Now here, angular momentum quantum number or azimuthal quantum number, this is designated by a term L. This L varies from 0, 1, 2, 3, and so on up to n minus 1. And this azimuthal quantum number or angular momentum quantum number, this tells us the shape of the orbitals. And if we say that L is equal to 0, this is the S orbital, L is equal to 1, P orbital, D orbital, F orbital, and so on. So this azimuthal quantum number tells us the shape of the orbital. And the maximum value is equal to n minus 1. So this is another quantum number which we call it as a azimuthal quantum number. The third quantum number is known as a magnetic quantum number. What is the magnetic quantum number? So now in the magnetic quantum number, it is designated by Mn. This is the magnetic quantum number due to its orbital motion. Because electron is orbiting here, if we say that this is the K shell, and in the K shell there are single orbital which we call it as the S orbital. In the L shell there are two orbitals which we call it as the S and P orbital. In the M shell there are three orbitals which we call it as the S, P and D orbital, and so on. So L is equal to 0 gives the S orbital, it means the electron is in the K shell. L is equal to 1, which we call it as a P orbital, it means the electron is in the P orbital, or which we call it as the L shell. So now in the L shell there are two orbitals. One is the S orbital and other is the P orbital. Similarly, for n is equal to 2, we have a three orbitals. For n is equal to 2, we have two orbitals S and P. For n is equal to 3, we have three orbitals S, P and D. This is for n is equal to 1, this is for n is equal to 2, n is equal to 3, n is equal to 4 and so on. So this gives you the shape. How many possible shapes? This magnetic quantum number gives the number of possible orientation of the electron in the s orbital or in the p orbital or in the d orbital. The s orbital is known as a spherical symmetric orbital. It means the particle is moving like a body is moving on the surface of the sphere. So this we call it as a spherical symmetry. So it means and the s orbital, this is the symmetric shell. It means it is like a particle is moving around the surface of the sphere. So which we call it as a spherical symmetry. So here ml, whose possible values is plus minus l, or the maximum value is equal to 2l plus 1. Maximum value of ml is equal to 2l plus 1. These are the maximum values of ml. For example, let's say here, for example, n is equal to 1 means principal quantum number is 1. This which we call it as a nucleus, and this is the K shell. N is equal to 1. It means here n is equal to 1, n is equal to 0. L is equal to 0 means this is the only s orbital. So in the s orbital, n is equal to 1, L is equal to 0, and ml is equal to 0. It means there is only a single possible orientation. So this ml, whose maximum value is this actually gives the number of possible orientations. This is the it gives the number of possible orientations. So now here, for n is equal to 2, let's say n is equal to 2, which we call it as a KL shell. So in the L shell, this is for n is equal to 1. And for n is equal to 2, n is equal to 2, the L has two possibilities. Either it is 0 or it is equal to 1. Because the possible values of L is equal to n minus 1. So here the L has two possible values. Either the electron may be here. It means this, it has two possible orbitals, which may be s orbital, which may be p orbital for n is equal to 2. In the s orbital, L is equal to 0. In the p orbital, L is equal to 1. So now, what is the value of ML, possible orientation? If we say that it is 1, the possible orientation is plus minus 1. Because the possible variation of the ML, which is equal to plus minus L, and for L is equal to 1, the possible orientation is plus minus 1. So here, therefore, the possible orientation is plus 1, 0 and minus 1. So there are three possible orientations for n is equal to 2 and l is equal to 1. So the possible orientation is plus 1, 0 and minus 1. And the shape of this p orbital is like a dumbbell shape. So this is the p orbital and this is the s orbital. So similarly, for n is equal to 3, n is equal to 3, this is M shell. So now in this M shell, we have a s orbital, we have a p orbital, we have a d orbital. It means here we have, for n is equal to 3, we have 3 orbitals. So s, p and d. It means if electron is in the d orbital here, so n is equal to 2, n is equal to 3, n is equal to 2, possible orientations of ml is equal to plus minus 2, and its values varies from plus 2, plus 1, 0, minus 1 and minus 2. So the possible orientation here is 5, 1, 2, 3, 4, 5. So it means this ml, which is one of the magnetic quantum number, which tells us the possible orientations of the electron motion, because the electron is revolving in the orbital. So here the fourth quantum number is spin quantum number. So now in the spin quantum number, you know that the electron is precessing in its own axis, because when we say that this is the nucleus, electron is orbiting around the nucleus, which we call it as an angular momentum quantum number. Similarly, the electron is spinning in its own axis. It means its spin may be up or may be down. If we say that the electron is precessing in the clockwise direction, the spin is down, and which we call it as a minus 1 by 2. And if the electron is precessing in anti-clockwise direction, the spin is up by using right hand rule. These curved fingers indicates the direction of the rotation, and this thumb pointing the direction of the spin. So here, for the clockwise rotation, the spin is down. For the anti-clock or counterclockwise direction, the spin is up. So the spin may be spin up, spin may be spin down. So the possibility of the spin is equal to plus minus 1 by 2 h bar. So this is known as a spin quantum number. So it means these are the four quantum numbers. These are the four fundamental quantum numbers which completely describe the motion of the electron in any orbital or in any shell, because you know that the electron in the atom, the central part is a nucleus, and the electron is orbiting around the nucleus. According to the Bohr's theory, that electron is orbiting around the nucleus. As long as it orbits, it does not radiate the energy. It only radiates the energy when it de-excites from higher level to the lower level. As long as it's revolve in the same level, it does not radiate the energy. So it means these levels are the quantized levels. These levels are known as a quantum states of the particle. And this is the fundamental theory which is based on the quantum mechanics, that according to the Bohr's theory, the electron remains in a certain quantum state. The states are not continuous states, states are the discrete states, and these discrete states are known as a quantum states. Now, in this quantum states, there are four fundamental quantum numbers which this electron has to be followed as long as it is moving in the orbital. So these are the quantum numbers. So now we are discussing, okay, what is the space quantization or the quantization of the angular momentum. So now we are discussing the space quantization. So now in the space quantization, you know that the one of the quantum number is the orbital angular momentum quantum number, which is quantized in space. For example, let's say we say that L is equal to, this is the reference direction which we call it as a z-axis. If we say that the electron is revolving here, this is the center which we call it as a nucleus, and this is the orbital in which the electron is revolving. If we say that the electron is revolving in this direction, clear? The angular momentum L is equal to R cross P. The angular momentum is known as R cross P. R is the radius of the orbital and P is the momentum of the electron, which we call it as a linear momentum. R cross P is its angular momentum. So angular momentum is a vector, position is a vector, linear momentum is a vector. So the angular momentum L is the product of R into P. So when the electron is revolving, as a resultant, it has an angular momentum which is normal to the plane of rotation. So the angular momentum is this. But when the electron is revolving in this orbit like that, if the orbital is this, the angular momentum is this. This is the angular momentum. This is the direction of the angular momentum. But if the electron is revolving like that, here, this is the direction of the angular momentum. So it means this angular momentum has different orientations. If we say that this is the center and this is the direction of the angular momentum, which we call it as the angular momentum vector L. This angular momentum is quantized in space. This angular momentum L is equal to, according to the space quantization, which we say that the angular momentum is quantized and the length of the vector angular momentum vector is L is equal to square root of L into L plus 1 H cut, H bar. And H cut is equal to H upon 2 pi, and you know that H is the Planck's constant. So here the L, whose magnitude is L into L plus 1 square root into H bar. For example, let's say this is the length of the angular momentum. For example, let's say this is the nucleus, electron is orbiting here. We say that the electron is orbiting in the p orbital. For p orbital, L is equal to 1. For p orbital, L is equal to 1. So now L is equal to 1 gives the vector whose length is this L. So now we have to show what is the length of that vector. So the length of that vector L is equal to L into L plus 1 H cut. So this can be written as 1 into 1 plus 1 H cut. This can be written as square root of 2 into H cut. This is the length of the vector. And this length, its projection is along the z-axis, along the reference axis. This is the angle of the vector which is making with the reference axis. Its projection is along this axis is known as mz into h cut, or which we call it as a Lz. Lz is the projection of the angular momentum along the reference axis. And this is also quantized in space. If we say that it is rotating in this direction, its mz is this. And this gives the possible orientations. This mz, which we call it as a, or you may call it as a MLH cut, which shows the magnetic quantum number, which is also quantized. So this also gives the possible orientations. It means, for example, let's say this is called the L. For example, L is equal to 1. The possible orientations of the ML is equal to plus 1, 0 and minus 1. Okay? It means the electron may be revolving like that. Its angular momentum is this. Electron may be revolving like that. Its angular electron may be revolving like that. Its angular momentum is this, and its projection is this. This ml is equal to plus 1. This ml is equal to 0. The electron, this may be the ml. Electron may be revolving like that. Ml is this, and its angular, this is minus 1. So there are three possible orientations of the ml. So this ml gives the number of possible orientations. For L is equal to 1, ML may be plus 1, ML may be 0, ML may be minus 1. So here the rotation is this positive, the rotation is this 0, the rotation is this gives the negative, minus 1. It means this gives you the positive, and this gives you the negative. Yeah. So this, the possible orientation is Lz. So Lz is the quantized angular momentum which gives the possible orientations of the angular momentum with reference to the z-axis. Because you know that in order to find out the possible orientation, there must be a certain reference axis. If you don't have a reference axis, then you cannot identify what is the direction of this. It means direction is to be measurable with a certain reference point. So this z-axis is to be considered as a reference point, and with respect to this reference point, we have to look at the different directions here, which may be along z, which may be plus 1, which may be 0, which may be minus 1. Now we have to look at what is the angle theta. So now if we look here, we have to find out the angle theta by using cos of angle theta. Here, if we look here, This is the reference z-axis. This is the L. It means this L is known, and this is the ML H cut, or we call it as a LZ is known, and this is the angle theta. This angle theta gives the direction of the angular momentum with respect to the reference axis. So how to get this direction here? This is L, clear? This is L. So here angle cos theta is known as a base upon hypotenuse. Base upon hypotenuse. And this base is equal to ML H cut divided by L. This L. So this ML H cut here is equal to cos theta is equal to ML H cut divided by L into L plus 1 square root into H cut. H cut cancel. Theta is equal to cos inverse ML divided by L into L plus 1 into this. So from this relation, you can find out easily the direction of the angular momentum with respect to reference axis. For example, L is equal to 1. ML is equal to, ML may be equal to 1. ML may be equal to 0. ML may be equal to minus 1. So you can find out easily the direction. Here, we may take these things. Theta is equal to cos inverse. L is equal to 1. ML is equal to 1. 1 upon 1 plus 1 into 1. It means this gives you 1 upon square root of 2 cos inverse. And this gives you theta is equal to 45 degrees. It means this indicates that for ML, L is equal to 1, ML is equal to 1, this is 45 degrees. You may take L is equal to 1, ML is equal to 0. So 0 upon something is equal to 0, and this gives you cos of inverse 0 is equal to 90 degree. So this vector gives you the 90 degree here. And again, you can take 1 minus 1 divided by this minus 1 upon square under root 2. This gives you the angle of 135. So this is known as a space quantization.